Welcome to The Explainer. Today, we're diving straight into the ultimate heavyweight bout of structural engineering. We're breaking down a fascinating study from the International Research Journal of Engineering and Technology, and they're tackling a massive question. When a severe seismic event strikes, which building's shape actually survives? In the red corner, we've got the traditional, everyday rectangle, and in the blue corner, the sleek, continuous circle. Let's find out which geometry is truly built to take a hit from Mother Nature. Now, we've got to set the stakes here because they are quite literally life and death. As our cities get more crowded, especially in highly active earthquake zones, we're building taller and denser than ever before. And sure, the building materials we use are absolutely crucial. But what this research points out is that a building's fundamental geometry is really our very first line of defense. The shape literally dictates how those crushing seismic forces travel through the frame. Okay, let's dive into this and look at some real-world examples. Take Mumbai's Antilia. It's towering, it's boxy, and it's aggressively angular. To stay up, it relies on some incredibly heavy-duty engineering tricks, just to manage the sheer stress that naturally funnels right into its corners. Now compare that to the Indira Gandhi Planetarium in Lucknow. Notice that continuous, spherical, aerodynamic form? There are no harsh edges there, which theoretically means forces can just wrap smoothly around the structure, instead of slamming directly into a flat wall.
So let's do a quick breakdown of our two contenders. Rectangles? Well, they're the undisputed kings of efficiency. Straight edges and 90-degree corners make planning and construction super cost-effective. You get to use up every single square inch of space. But, and it's a big but, that angular design creates massive stress traps right at the corners. Circles, on the other hand, are structurally kind of the dream. Their continuous shape promises a perfectly uniform stress distribution, and no corners means practically zero twisting forces, which is exactly what tears buildings apart. The catch? Curved walls are notoriously complex and super expensive to build. Now, how do we settle this debate without, actually demolishing real skyscrapers? The researchers set up a highly rigorous computerized stress test using a piece of advanced software called STAAD-Pro. This isn't just a basic 3D drawing tool, it's a heavy-duty computational arena. It simulates exactly how different materials and shapes will buckle, sway, and react when they're slammed by the dynamic forces of a major earthquake. All right, let's bring out the first contender in our virtual arena, the rectangular model. The researchers built a massive 15-story structure, ground plus 14 floors, and they didn't hold back. They used high-grade concrete, heavy steel reinforcement, and gave it a footprint of exactly 750 square meters. Then, they virtually dropped it straight into a simulated seismic Zone V. Just for context, Zone V is the most extreme earthquake environment you can get. We're talking the absolute highest risk of catastrophic ground shaking.
And stepping into the ring, here's our challenger. To make sure this was a perfectly fair fight, the researchers built a circular model with the exact same constraints. It's also 15 stories tall. It's built with identical grades of concrete and steel. It's resting on the exact same hard, rocky soil, and it occupies that precise 750 square meter footprint. The only thing changing in this massive simulation is the geometric shape. We're isolating the structure to see if the circle actually lives up to the hype.
Okay, before we jump into the results, let's do a quick jargon buster for our first big metric. You're going to hear the term maximum displacement a lot. Simply put, it's the exact distance a building physically sways or shifts to the side during a quake. Think of holding a ruler upright on a desk and shaking the desk. How far the top of the ruler whips back and forth, that's your displacement. Keeping that lateral sway to an absolute minimum is critical, because too much sway and the whole thing snaps. Now, what's really interesting about this data is the stark contrast we see right out of the gate. When the software measured the sway in the z direction, the rectangular building displaced by roughly 279 millimeters. But check out the circular building. It only shifted about 164 millimeters. The continuous shape of the circle absorbed and scattered that kinetic energy so well that it barely swayed compared to the rectangular box. The circle is already proving its theoretical advantage in a massive way.
And if you thought that z-direction data was wild, the x-direction is even more dramatic. Measuring the lateral shift along that axis, the simulation showed the rectangular building swayed a staggering 61.10% more than the circle. I mean, just imagine being on the 15th floor during that level of shaking. Over 60% more violent swaying, all because the building has flat walls and sharp corners. When it comes to lateral stability and keeping the people inside safe, the circle absolutely crushes the rectangle here.
Now, let's shift our focus from the very top of the building, where it sways, all the way down to the foundation. Our next critical metric is base shear. This is the maximum expected lateral force acting right at the base of the structure. Think of it like a brutal, horizontal slicing motion caused by the ground violently shaking beneath it. If a building can't handle its base shear, it literally gets sheared completely off its foundation.
But here's where the study gets a bit more nuanced, which honestly makes it so much more credible. You'd probably assume the circle wins every single category, right? Well, the base shear data tells a slightly different story. The rectangular building absorbed about 7,800 kilonewtons of force, but the circular building actually took on a bit more, clocking in at over 8,300 kilonewtons. So surprisingly, the circular building doesn't sweep the board in every single metric.
To put a fine point on it, the circular structure faces a 6.84% higher base shear than the rectangular one under the exact same earthquake conditions. And this is a brilliant reminder that engineering is always a game of trade-offs. Sure, the circle reduces that terrifying sway up at the top, but the way its mass and shape are distributed means it takes a slightly harder horizontal hit down at the bottom. Architects and engineers actually have to build beefier foundations for circular towers just to account for this.
And that leads us perfectly into our final crucial metric, support reaction. While base shear is the horizontal force attacking the building, the support reaction is the counterforce. It's the energy exerted by the foundation and the earth itself pushing back up to keep the building standing upright against gravity and those chaotic seismic loads. Basically, a lower support reaction means the building is resting more comfortably and stably on its foundation, so it doesn't have to fight as hard to stay up. So the crucial point is how these two shapes actually handle these massive foundation loads. Looking at the Y-direction support reaction, the circular building needs about 6,500 kilonewtons of support. But the rectangular structure, it demands over 8,000 kilonewtons. That means the rectangular building requires a massive 23.26% more support reaction just to avoid collapsing. Its angular geometry is literally forcing the foundation to work nearly a quarter harder to survive the quake. To really lock this concept in, picture how energy flows. When seismic waves hit a continuous circle, the energy just wraps around it smoothly. But think about straight edges and sharp right angles. They act like dangerous little funnels, trapping and concentrating all that seismic stress. Because the energy just slams into these 90-degree corners, it creates massive localized pressure. And that's exactly what drives up the need for those extreme support reactions at the base. The geometry is quite literally fighting against itself. So what's the final verdict? After running the numbers on displacement, base shear, and support reactions, the researchers made it crystal clear. Circular geometry wins. Yes, it takes a slightly higher base shear, but its ability to evenly distribute stress makes it vastly superior. It sways dramatically less, and it rests far more stably on its foundation. In a catastrophic Zone V earthquake, the circular building is, without a doubt, the safer structure.
This whole study is such a fantastic reminder that architecture isn't just about looking good or maximizing office space. It is deeply tied to physics and, ultimately, our survival. Next time you're walking downtown, look up at your city's skyline. Look past the glass and the steel, look at the geometry itself, and ask yourself, which of these shapes are actually built to survive? It'll completely change how you see the structural boxes we live and work in every single day. Thanks for joining me on this explainer, and keep questioning the world around you.